Today I will talk about voxel-based Eigenstrain reconstruction for the full field reconstruction of residual stresses. Previously I presented a tomographic Eigenstrain reconstruction of residual stresses last year here in this meeting, and I didn't talk about theoretical background of this method. This year I will try to give you the theoretical background of this tomographic Eigenstrain reconstruction with some case studies. Okay, tomographic Eigenstrain reconstruction relies on planar distribution of residual elastic strains quantified using synchrone diffraction. The benefit of this approach is ability to reconstruct full field distribution of residual stresses using very limited amount of experimental data. The method also provides information about all components of residual stresses and eigenstrains, and achieving this kind of detail using very limited amount of data is highly beneficial in our field. So we continue our development on this field. Let's start with Eigenstrain theory. It was introduced by Mura in 1987. According to this theory, irregular distribution of permanent plastic strains causes the formation of residual stresses. These permanent plastic strains are called eigenstrains. Mapping the distribution of eigenstrains allows the calculation of residual stresses using linear elastic numerical models. Okay, how do we implement eigenstrain theory? We see tensor of eigenstrains and how eigenstrains are implemented to the Hooke's law in the matrix form. Here we subtract eigenstrains from total strain, and as we do this, problem turns into a linear elastic problem. But in order to do this, we need to map eigenstrains using experimental data. How we do this? We use independent solutions of basis functions that are stored in C matrix. And here we have U vector that stores experimental data that will be used for mapping eigenstrains. And the A vector accommodates unknown weights of independent solutions of weight functions. So linear solution of this problem gives us the weights of independent solutions of basis functions. At the end, based on the principle of superposition, when you sum them up, it gives you state of stress and strains. So in a case study, I will show how we do it. Here we have finite length development. It is divided into half by non-contact cutting. How it happens? It happens by EDM cutting technique. And we do this cutting from plane A. And we use contact profilometry or optical profilometry, but for large components, it is ideal to use contact profilometry. Using contact profilometry, we use relaxation displacements due to stress relaxation on the surface, on the cut surface. But I want to mention that this information belongs to out of displacements, and similarly, the stresses relaxed are assumed to be only out of plane stresses. And this data is used for the determination of distribution of eigenstrains within this symmetric domain. How we do this in mathematical terms is that we use Chebyshev polynomials to map eigenstrains in two-dimensional plane, and we use two additional guiding functions to focus eigenstrains in the welt beam. These are Gauss function to focus Eigenstrain in the planar distribution, and it is near or Hill function to focus the distribution in longitudinal direction. Accordingly, we use in this formulation two guiding functions. So what happens when we import the calculated eigenstrains into linear elastic finite element model? It gives us residual elastic strains and residual stresses. And the good thing about this method is we are able to map stress state after different processing conditions. So in here you see before cutting and after cutting state. And now we did some improvements. We developed Voxel-based Eigenstrain reconstruction technique. It was published recently. This technique allows overcoming the limitations of previous method. The limitations of previous method was the need for using guiding functions. In this approach, we don't need it, and we divide the domain into voxel domains. We solve radial basis functions independently as centered to the voxels, and the same linear solution is performed this time without need of any guiding function, and we get very accurate reconstruction during numerical experimentations. You see here a reference case and the reconstruction, and its observations show that increasing the Voxel density increases the performance of the reconstruction. Here I will show some numerical experiments in a body that satisfies continuous processing conditions. That means eigenstrains distribute in a plane-wise, but they are kept constant through the thickness. In this condition, what we do is we remove this material is first connected to a base. We remove it from the base. Displacements after removal of the body from its fixed base are measured and used for the determination of eigenstrains. So in here, experimental data is the displacements obtained from the top surface of the numerical experiment. We see the results. Numerical line profiles are belonging to the volume diagonal, and they show very accurate reconstruction of all components of eigenstrains and residual stresses. We repeated the numerical experiment in a body that satisfies discontinuous processing conditions. In this case, as you see on the top left, this time eigenstrains also varies through the thickness, and again, three normal components of eigenstrains distribute in three axes. Same experimentation and quantifications were applied. Again, we obtained very accurate reconstruction of all components of residual stresses, but we had some slight deviations in some components of eigenstrain, but it doesn't matter in this case because visually we don't see any difference, and reconstruction of stresses are very accurate. We performed a validation using bent specimen. It is a titanium alloy, and results show characteristics of bending residual stress clearly. Details can be found in the paper. And in another case study, this time we applied the same data, same weld experimental data for voxel-based Eigenstrain reconstruction technique. Before doing that, we performed a numerical experiment. In this numerical experiment, we imported an Eigenstrain state with 3 components distributed in all 3 axes and calculated residual elastic strains belonging to this Eigenstrain distribution. And we did similar cutting process, but this time numerically, from the front face of the domain only, and performed reconstruction. Of course, first we determined the distribution of eigenstrains, and then quantified residual elastic strains. And so after reconstruction, what we did, we remapped 3 components of eigenstrains and 6 components of residual stresses. And in here I show you their magnitudes. And yes, this experimentation showed that we can get very good reconstruction in the whole volume using data only from the front face. In tomographic reconstruction, we use data from different lasers, but in order to challenge this model, in this test, I use only data from front face and try to reconstruct the components in the whole body. So what we get, okay, here from this result, we see what we can expect from a real case. So we have discontinuously processed development. This is a finite length development, the previous data. And yes, according to results, we see that eigenstrains distribute around the weld zone. This is an expected thing. This theoretically validates what we did. In addition, residual stresses are calculated. Here we see longitudinal component because we have longitudinal component of data. We have displacements belonging to the z-axis. So these are the residual stresses parallel to the experimental data. And we look von Mises criterion. So this is a nickel alloy, and magnitudes show that we don't violate von Mises criterion. Okay, now I will show you a neutron diffraction experimental validation. For this validation, we measured 2 components of residual elastic strains that are X and Y, but I want to remind again, we have data for Z component of experimental, we have experimental data for Z component of displacements. So this is a challenging condition. We are challenging the model to quantify stresses different than the component of experimental data. Here are the results. Okay, this is a finite length band. That means weld bead travels up to a point and it terminates. It is around 50 millimeters from the cut surface. So the right side belongs to cut face, and we penetrate inside the body. And these measurements are taken, neutron diffraction measurements are taken after cutting the plate. So this is the conditions after cutting. And what then can we conclude is that both model calculations and neutron diffraction quantifications show similar distribution. The sign and the magnitude of these stress components switch at the end of finite length weld bead. This is a good result because we can quantify a characteristic property of distribution of residual stresses away from experimental data. This is the point. And that's it. Thank you for listening.